Welcome back to the course Sustainable Energy and Green AI. This is the final part of the lecture on IoT for data collection and management. Well, in the previous two parts, we built a solid foundation for understanding how IoT supports sustainable energy systems. In Didactic Unit 1, we introduced IoT as data engine for AI and examined its role in smart grids, renewable energy monitoring, and energy efficient buildings. In Didactic Unit 2, we focused on the technical aspects, including IoT architecture, sensor ecosystems, communication protocols, and data management, and discuss how AI can enhance sustainability in buildings. Today, we bring these elements together by focusing on smart sustainable buildings. Their IoT data enables intelligent control, predictive maintenance, and energy optimization. This is where the concepts came into life in real-world built environments. Let's start by defining what we mean by a smart, sustainable building. A smart building uses real-time data to automate and optimize its operations. It responds dynamically to changes in occupancy, weather, and energy demand. For example, we can adjust lighting and HVAC systems based on whether rooms are occupied or not and how much sunlight is coming in. A sustainable building, on the other hand, is designed to minimize its environmental impact. It reduces energy consumption, lowers carbon emissions, and uses resources like water more efficiently. The IoT plays a central role here. It acts as data engine, collecting, transmitting, and analyzing information from various systems to enable intelligent decision making. Key systems to benefit from IoT integration include HVAC systems that adjust based on occupancy and air quality, lighting, automated lighting that responds to natural light and usage pattern, water management, leak detection and usage monitoring, renewable energy integration, system like rooftop solar panels that feed data into building energy management platforms. Occupancy and access control, smart sensor and badges that track movement and access. Together, these systems create a building that's not just efficient, but intelligent, adaptive, and environmentally responsible. Let's start with the concept of demand side management or DSM. DSM is all about making buildings smarter and more responsive to the energy grid. Instead of passively consuming electricity, smart buildings actively manage when and how they use energy. This helps reduce costs, improve efficiency, and support grid stability, especially as we integrate more renewable energy sources. One of the key DSM techniques is load shifting. So, what does it do? Load shifting moves energy consumption from peak hours to off peak hours without reducing the total energy used. How does it work? It uses smart scheduling of systems like HVAC or EV charging and industrial processes combined with automation and real time pricing signals. What does it reduce? Primarily, it lowers peak demand on the grid and helps cut energy cost by taking advantage of cheaper off-peak tariffs. What does it complement? Load shifting works hand in hand with peak shaving and demand response programs, creating a more balanced and efficient energy profile. And the ultimate goal? To optimize energy use timing, reduce cost, and support grid stability, all without sacrificing comfort or productivity. Now let's move to the second technique, peak shaving. Unlike log shifting, this moves energy use to another time. Peak shaving actually reduces the peak itself. How? By using on-site energy storage like batteries or distributed generation such as solar panels, or supply part of the demand during the high load periods. Sometimes it also involves temporarily reducing non-critical loads. What does this achieve? It lowers peak demand charges on electricity bills and reduces stress on the grid. Peak shaving works best when combined with load shifting because together they flatten and redistribute energy demand, making the building more efficient and cost effective. The ultimate goal is to smooth out the demand curve and minimize cost without compromising essential operations. Finally, let's talk about load shedding. This is the more of an emergency and last resort measure. When the grid is under severe stress or during critical events, load shedding temporarily turns off or reduces non essential loads like decorative lighting or certain HVAC zones. It's fast, automated, and helps prevent blackouts. What does it lower? Immediate emergency consumption during critical periods, which helps maintain grid stability. And it complements both load shifting and peak shaving by acting as a backup when other strategies aren't enough. The goal here is simple: provide rapid relief to the grid and keep the system stable. Together, these three techniques, load shifting, peak shaving, and load shedding, make smart building active players in energy management, reducing cost for owners and supporting a more resilient, sustainable energy system. Artificial intelligence plays a critical role in making DSM strategies effective. For load shifting, AI uses reinforcement learning and genetic algorithms to schedule loads like HVAC and EV charging at the best times. For peak shaving, predictive models such as neural networks and LSTM forecast demand peaks, while optimizing algorithms decide when to discharge batteries or use on site generation. Load shedding relies on rule based AI and fuzzy logic to prioritize which loads to cut during the emergencies, and reinforcement learning helps improve these decisions over time. Across all techniques, machine learning and deep learning are used for forecasting, while meta-heuristic algorithms handle complex optimization problems. Together, these AI tools make smart buildings truly responsive to the grid. Intelligent Fault Detection and Diagnostics, or IFDD, is proactive approach to maintaining building systems. Instead of waiting for something to break, IFDD continuously monitors data from sensors, temperature, pressure, airflow, energy consumption, and so on, and looks for patterns that indicate a problem. How does it work? IFDD uses advanced AI techniques like machine learning and pattern recognition to detect anomalies. For example, if an HVAC system suddenly consumes more energy than usual or airflow drops unexpectedly, the system flags it as a potential fault. There are several techniques involved. Energy usage analysis helps identify abnormal usage patterns. Sensor data monitoring tracks real time performance, and fault signature analysis uses historical data to recognize specific fault patterns. Data driven anomaly detection is particularly powerful because it learns what normal looks like and alerts us when something deviates. The benefits are significant: improved energy efficiency, reduced downtime, and better occupant comfort. By catching issues early, IFDD prevents costly failures and ensures the building operates peak performance. AI is the engine that powers IFDD. Let's break it down. First, supervised methods like decision trees, random forests, support vector machines, and neural networks are used when we have labeled data. meaning we know which pattern corresponds to faults. These models learn from historical examples and can classify new data accurately. But what if labeled data is scarce? Then there's unsupervised methods come in. Techniques like clustering and principal component analysis group data points and detect anomalies without prior labels. This is useful for discovering unknown fault patterns. In many real world cases, we use hybrid approaches, such as semi supervised learning, which combine both methods to handle limited labeled data effectively. Finally, these models aren't static. Continuous refinement is essential. As new data comes in, the system retrains and improves, reducing false alarms and increasing reliability. This adaptivity makes AI-driven IFDD cornerstone of modern building automation. Let's talk about predictive maintenance. It's all about moving from reactive to proactive strategies. Instead of fixing equipment after it fails, we predict when it's likely to fail and schedule maintenance at the optimal time. How is this possible? Through IoT sensors and AI. Sensors collect data on temperature, vibration, energy use, and other performance indicators. AI algorithms then analyze this data to identify patterns that signal wear or degradation. The benefits are huge: reduced downtime, lower maintenance costs, improved safety, and better resource planning. For example, if motor shows vibration patterns that historically precede failure, the system alerts the maintenance team before the breakdown happens. Techniques include machine learning models like decision trees and neural networks, Bayesian networks for probabilistic reasoning, and deep learning for complex pattern recognition. Statistical methods like variable analysis and prognosis estimate the remaining useful time of equipment. In short, predictive maintenance ensures reliability, saves money, and keeps operations running smoothly. To wrap up, let's connect all the pieces together. IoT provides the foundation by collecting real time data from sensors on energy use, environmental conditions, and equipment health. This data is transmitted and managed through the edge and cloud platforms, forming the backbone of smart building operations. AI then transforms this data into actionable insights. Through demand side management, we optimize energy use patterns, reducing cost and supporting grid stability. Intelligent fault detection ensures that issues are identified before they escalate, improving efficiency and comfort. And predictive maintenance allows us to plan interventions before failure occur, reducing downtime and extending equipment life. The result is a building that is not only smart but sustainable, consuming less energy, emitting fewer greenhouse gases, and providing a better experience for occupants. This synergy of IoT and AI is the key to achieving performance, resilience, and sustainability in modern energy systems. Thank you, and my congratulations because you have finished the first lecture of this course.